Welcome, everyone. This week's showcase is from the Advanced Analytics team, and usually we work on MATLAB and a couple other related Greenplum technologies, but this time I'm going to talk to you about a special project that we've been working on for, well, it's pretty much wrapped up now, but we worked on it for maybe 2 months or so. So to give you some background first, there's this, the main project this is related to is this Gaia database where I've put up some links here. There's lots of articles on, basically they've mapped like over 1.7 billion stars in different, some of them in other galaxies, some of them in ours, all over the sky, and they've got different properties with them. And they've got a prototype up where you can search that database online, but they're looking to keep scaling up this data, and they want, Greenplum's one of the technologies they're thinking about using to do that. The specific query that they were interested in speeding up has to do with, well, in general, queries using an open source library on GitHub called Q3C. It stands for Quad Tree Cubed. And I'm going to tell you in a minute what that does and how it works. But basically, some of the slowest and most complex operations you can do with that, usually it's used for searching on a spatial sphere geometry. In particular, in astronomy, they're using it to search on the celestial sphere. So if you look out at the sky, you can imagine the entire sky is a big sphere, and you can use two-dimensional spherical coordinates to see where the stars are in the sky. For these purposes, we don't care about how far away they are, so depth is just ignored here. And the last link is the academic paper that they published on how to get this to work, which they did it by parallelizing. They ran a whole bunch of instances of Greenplum just on a single machine, basically. So they had their own kind of hacked together way of parallelizing it. And
I think you meant Postgres, right? They did a whole bunch of parallel Postgres, not
did I say
parallel
Greenplum?
Yeah.
Yes, sorry, I meant, yeah, they had a bunch of Postgres instances running in parallel, but just on one machine. And so this is the query that they came to us wanting to optimize. Basically, they have two of these tables, one with about 1.1 billion rows and one with 1.7 billion rows, and they want to join them together. Every row in it represents a particular star in the sky, and it has a lot of information about its properties. But basically, the only two fields that we're really interested in are called RA and DEC. It stands for right ascension and declination. And it's basically just the location of the star on this celestial sphere. So each row in one of these tables corresponds to a point on this sphere, basically, with information. And you join the two tables by saying we want to join on points within a certain distance of each other. And the distance is passed in as this. So you pass in the RA and the DEC of the first table, of the second table, and then this last argument to Q3C join is a radius, which is here saying 0.5 arc seconds. So because it's on a curved surface, it's just given as an angle. And this Q3C join just returns true or false, and then you can use it in a where clause to select. And if you did this naively without any optimization, then you'd expect it would have to run this Q3C join function, which is a fairly complex function that has to traverse a quad tree, which I'll explain in a minute. It has to run that on every row in the product of those two databases. So basically like 1.9 times 10 to the 18th rows, which is going to take you millions of years, even if it's doing each row fairly quickly. So first, I'm going to kind of start at the end and just go over the performance results we were eventually able to get out after a lot of tweaking and experimenting. And then I'll kind of go over more specifically what we did, how we set up the database, the proposed user-friendly interface that we want to make for this, and possible future improvements. So the most exciting thing, I guess, or the most impressive thing, is that so far with the data sizes we've tested, which is all the way up to the entire 1 billion row size, we've seen linear scalability with the data size. Now, it's possible, there are theoretical reasons to believe that it might be n log n, O of n log n instead of O of n, but if that's true, we haven't really seen much indication of it. Like it's a very good fit to a line so far. And also, in this one, I'm more sure of definitely linear scalability with the cluster size, even though we've only tested it on 2 different cluster sizes, 16 segments and 24 segments. But we saw a pretty consistent 50% increase in, it ran 50% faster on the 24 segments, no matter what data size we gave it, no matter what input we gave it. And on the 24 segments, which is a cluster of 3 machines, it took under 3 hours. So that's coming all the way down. Now they had gotten it, the best in that academic paper, they had gotten it down from millions of years to 5.5 hours was the best time they reported. And they had a terabyte of RAM on their machine, about the same amount of hard drive space. We might have, I guess between 3 machines, we might technically have more CPU than them, but that's kind of the only advantage. And then this would cut down, like if we doubled the cluster size on top of that, it should cut down to half of that time. And even though we ran this on 100 gigabyte machines, we never really could get it to use more than 20 gigs of RAM, so it should run just the same on 32 gigabyte machines. So here's for the cluster of 3 machines. You can see the 2.9 hours, and then this is the line that it fits to. And you can see that, you know, the last data point's slightly above the line, but some of these are slightly above, some of them are slightly below, but it was a very good fit. If we had a data set that was 10 billion rows, which is something they eventually want to do, we could test with that and see whether it keeps curving up a little bit here, if it continues to be linear. But that's something for future experimentation. And this is for only 2 segment hosts, very similar line. It's basically just the enter line is shifted by 50% faster. And oh yeah, here is some charts with the actual number of rows we used, and basically we took like 10% of the data set, 1%, 0.1%, etc. And going from the 16 segments to 24 segments, you get this scale factor increase. And 4.5 hours was the best time with 16 segments, which is already, even with just 2 hosts, it already beat the 5.5 hours. So we don't need the 3, but it's even faster with the 3. So quad trees. Now I'm going to explain what this Q3C join library does and why Greenplum doesn't out of the box handle it very well. So usually often when you do spatial searches, you can use quad trees to store the data. It's a data structure you can store things in so that you can do fast searches within radiuses of them. And what it does is it takes the entire two-dimensional plane, breaks it up into four quadrants, and those become the four children of the root node of the tree. And then you break each of those quadrants into four more quadrants, and those become the children of those nodes, and etc. And one reason this is very useful is, um, like in this case, the stars in the sky are not homogeneous. It's not like you just have the same amount of stars everywhere you look. Some regions are very dense and some are very sparse. So you might want to have some nodes that have a much greater depth, and you can see a very high resolution in those areas, and then others that are kind of shallow and only go down a little bit, and those would be the sparse regions. So you don't have to take up more size than you need, and you can quickly search this tree in logarithmic time if you know roughly where you're searching. And it just kind of narrows it down more and more spatially as you go down the tree. And so this is a picture I drew so the cubed part of Q3 of quad tree cubed is that they do the quad tree on a cube. So each of the six faces of the cube is its own quad tree, and then they literally just warp the cube and map it onto a sphere, so it looks something like this. Putting these three together, hopefully you can kind of visualize what it's doing. It's basically just a bunch of trigonometric functions to do this mapping. And once you've done this, you have all these cells called IPIC that they call IPIC cells. And each, so every time you have a particular RA and DEC, those two coordinates pointing to someplace in the sphere, you can convert that into a unique IPICS number. Well, you can tell which IPIC cell that point is in, and it's this 64-bit number. The first digit's unused, and then the next 30 represents which of the six faces of the cube you're on, and then the rest just alternate basically X and Y coordinates within a particular face. So, and you can also think of it as every 2 bits is telling you which of the 4 nodes of the tree to go down. So it's mapping out like a path through the quad tree. Whoops. So by the time we had come up with I guess before maybe I should say, so this was already in place before Greenplum, and the idea was that you're supposed to use it with a B-tree index, and that could help you iterate through the rows of one table and then very quickly just look up other rows in the other table, so you didn't have to iterate through both of them. But Greenplum doesn't handle indexes or range joins very well, and that's what this is basically a range join, because it's taking a point and it's looking for all the points within a particular radius, and inside the Q3C join function, it calls a bunch of nearby functions to tell you which IPIC cells, like a range of IPIC cells basically, and then it requests all of those IPIC cells. It's supposed to use the index to request them, but the first challenge we faced was even trying to get Greenplum to use the index, because if it doesn't use the index, it just was never returning. And then the next big challenge was once it was using the index, it was doing everything on every segment. There wasn't an easy way to get it to actually parallelize and do different parts on different segments. And I'll talk about how we got that to work.
How does this encoding scheme even fit with the B tree? I feel like it fits better with like something like R tree, because of the like there is not a well-defined ordering, but it does have like proximity defined for this encoding scheme. So I thought it fits better, like quad tree, for example. Your indexing is supposed to like fit with a quad tree, which is a natural fit with like gist and R tree.
Well, the way the inside the Q3C join function, there's this internal function in the Q3C library called nearby it. And if you have a point, it just returns, it's basically, it returns 4 different IPIX ranges. I guess one of the special properties that makes this, I'm not sure if maybe R trees could work better or the same or whatever. I don't really know how those work actually. But I think one of the reasons that this works is because there's this special property that, like, if you specify a range of IPIX numbers, everything between, like, if you specify a range from the top left corner, I might be getting in the directions wrong, but like the top left corner to the bottom right corner of one of these IPIX cells, all of the IPIX numbers in between will be in that cell. So you can specify regions by using ranges. So I think that's the thing that allows the B tree to work, is because every one of these regions maps to a range, a continuous range in IPIX numbers. Does that make sense?
Yeah.
Okay. So after we got all of this to work, we realized it's a very hairy looking query that a user would never want to enter. So the first thing I'm going to reassure them of before I show them the details is that you're not going to actually have to type anything except this. So currently we've just got like SQL files laying around that where we run all the commands in them, but we're thinking ideally we would put it into an initialization function and then an actual join function that replaces like GP underscore Q3C join instead of Q3C join. And the initialization would basically set up the tables and distribute them in the right way. It would set up this B tree index and cluster it. And then the join function would change a bunch of gucks, run the optimized version of the query, and then restore all of the settings back to. So now, let's see how much time I got. Okay, so let me discuss the actual setup of how this all works. So originally we were thinking, okay, you can parallelize it by taking slices or something, but none of that works quite as well as just using the structure of the Q3C library itself. And so what I ended up doing, which works very well, is taking groups of IPIX cells, basically. If you go to this IPIX number and you just take the most significant bits up to a certain point, then you get a region of IPIX cells which ignores the higher resolution stuff. And that basically represents a node that's fairly high up in this quad tree. And so we define these regions just based on shifting the bits in the IPIX number and then distribute it into different segments based on that. And then there's an additional problem, which if you're searching near a boundary, you might have to look at points in the neighboring boundary. So just because you distribute them by those regions doesn't guarantee that this region and the region next to it are going to be on the same segment. And then we solved that problem by allowing it to redistribute points that are close to the boundary ahead of time. And that's why the query got a little more complex. But basically, you break it into these regions. We add the region, so and then add the region column, materialize it for each table, distribute it by region, and we make this, like, those are the steps for setting it up. And then these are the actual commands you'd need for that, analyze the tables so that it can form a better plan. And then for the query itself, we call ahead of time, like the first step is call this nearby it function, which is also part of the Q3C library. to get all of those 4 ranges back, and it returns it as you pass the last parameter is like a number from 0 to 7, so it gives you like min or max of the 4 different ranges, and that corresponds to 4 different or 8 different regions at most. And then union all those results together. So it's basically sucking in like all of the nearby, the region that you're searching in, plus any regions that contain nearby IPIC cells that you might also have to search in. And then once all of that is put together, you have to remove the duplicates to streamline things. And then you perform the query, but with this extra region equals region on this segmented version of the table and the second table. And step 4 in between, the way we designed it, should happen automatically, is Greenplum will just redistribute the data that's near the boundaries. Whoops, I think. So this is what the end query ended up looking like. Here, I just found this by kind of playing around, that 49 bits of shifting kind of worked pretty well. That leaves these regions, that means each of these regions is like a 15-bit number, and 3 of those bits are used for the face of the cube, and then the other 12 bits tell you where to go down in that tree. So it unions all this stuff together, and then it does the optimized version of the query with where region equals region. And the only other, I think this is my last slide. The only thing I wanted to show you was we had to adjust, especially, so the last big challenge was actually trying to get the planner or Orca to actually implement the plan that we wanted. So for a long time, I knew exactly how I wanted it to work, but I couldn't convince Orca or the planner to do that. And so the QP team helped me a lot with trying to adjust all these gucks. So we only really got it, well, we did get it to work both with Orca and Planner eventually, but it worked better with Planner, so turn the optimizer off. That optimizes a lot of queries well, but this one, because there's so much optimization that it's not expecting already, it just kind of conflicts with it. And turn hash join off, merge join off, because this has to do a nested loop join, which is unusual, but that's what works. And these other things, the memory, that's a whole other story, but it might be optional. But that's basically it. Any questions on any of that?
Have you considered using different table types, and have you also considered using partition tables?
Yeah, we did play around with append optimized tables. We also tried partition tables. Partition tables are designed for a somewhat different situation. Sridhar and I both tried to get them to work, and then eventually we realized it's just not really designed for this. I guess the main thing is because we wanted our regions to be each region on a separate segment, and partitioned is more designed for, like, if each region were a sub-partition, you'd want that to be on all segments. And so it's kind of a different situation. And then we tried append optimize, compressed, a couple different variations of that. But one of the big problems, so with Orca, it actually does run the fastest with regular append optimized. But with Planner, it ran faster with, it couldn't use the index for some reason. Planner,
you will lose the index scan, but you seem to be a really hard band to convince. I see that from your GUC, you are trying really hard to convince Planner to use the index,
right?
Like by setting insane cost on normal table scans.
That's because pretty much nothing is ever going to return unless you use the index. That's one thing that we found, is that's the most essential part of this. Like, if you don't use the index, then it's always going to be O of n squared, and with a large data size, it just runs way too long. And many times when I was talking about this to different people in Pivotal, they were all like, why do you want a nested loop join? Why don't you just forget about the index? And
Oh, they're just not educated. That's fine.
a few times I was like, okay, let's try it. But every time we tried it, it just never returned. So, and I did think from the beginning that that was not going to work, but yeah. Any other questions?
Great. The question is for optimization further, how large is your region? Will making the region smaller be able to make this one running even faster or not? I mean, is there any relationship between how large is your region comparing to the query performance?
Possibly. I don't think it'll make a huge difference. The main thing that it would help with is skew, because the main purpose of the index already speeds it up a lot. The main purposes of the regions is to be able to parallelize it on segments. If you pick regions where there's a lot of data in one segment and not a lot of data in another segment, then it could end up taking more, like the longest segment is going to be the limiting factor. So it doesn't matter if you had 16 segments and 15 of them ran really fast. If one of them's running slowly, then you're screwed. And if you have smaller regions, then I think there's less of a chance of something like that happening, because, or actually, no, I think I said it backwards. I think if you have, well, I think maybe there's a danger both ways. If it's too small or too large, you could have the skew be a problem. Like one of the problems we had with having segments too large, like at first I just tried 6, like one for each face, and I tried like 24 and stuff like that. And the problem was just there's a lot of stars in one part of the sky and not a lot of stars in another, so there's a lot of skew. But if you had them too small, then I think you might run into the same problem where you get, like with a small sample size, maybe there's a lot of variation. Well, I guess smaller is better for that, but you don't want to get small enough to where it's comparable to your search radius. We ended up using, it's roughly about 1 degree. Each region was about 1 degree in radius, and the searching they're doing is a half of an arc second, so about 4,000 times, or thousands of times smaller than that.
I see. Interesting. Yeah, so if I read it right, basically do a index lookup plan, index lookup join plan, something like that.
Yeah, it's a nested loop join, which sounds bad, but then because it's using the index, it only really has to iterate through one of the tables. The B tree, I was expecting an n log n time, since I think to look up in a B tree, it should be logarithmic, but I don't know, empirically, that when we measured it, it just seems to scale linearly. So maybe we're just not hitting the limit of that yet.
Yeah, maybe the tree lookup is so fast. The level
Right.
of the tree is
Yeah,
so
maybe that's just not the
You
limiting
just have a
factor.
shallow tree, probably.
probably, yeah.
That could be, yeah. All right. Thanks everyone for joining, and have a good lunch.
Thank you.
Thank you, Domino.
Thank you.